So to determine the energy of electron in a shell, we have to remember the basic concept that energy of electron will constitute kinetic energy and potential energy. So we start by putting in place the equation for kinetic energy and potential energy. So total energy of electron in any given shell will be equal to the sum of kinetic energy plus potential energy, and we therefore put up equation 26 that energy is equal to kinetic energy, which is a half mv squared, plus potential energy, which is Z e squared over 4 pi permittivity R. So if we look at this equation, remember that our interest is to determine the energy of electron in a given shell. But this equation so far does not have the value of the shell, so we have to introduce the value of n into this equation. So we go to first in step 2, we know that as the electron is in particular orbit, it is acted upon by two equal forces, which are the forces of attraction and the forces of repulsion. In other words, centripetal force and centrifugal force. So since these two forces must be equal, so we get the equation for centripetal force is equal to centrifugal force, which are Z e squared over 4 pi permittivity R squared is equal to mv squared over R. So from this equation, we get the equation for mv squared, and we make mv squared the subject. So we have mv squared is equal to Z e squared over 4 pi permittivity R. And we see that mv squared is close to the expression of kinetic energy. The only thing that is missing is a half. So we multiply both left hand side and right hand side by a half. So we get a half mv squared is equal to Z e squared over 8 pi permittivity R. So since the equation 27 is similar to the expression of kinetic energy, we go back to equation 26 and substitute the value of a half mv squared by the equivalent of Z e squared over 8 pi permittivity R. So we now get the equation 28, but remember now the first component is a half of the second component. So it's like we are taking 1 over 8 minus 1 over 4. So we get minus 1 over 8 if you do that calculation. So we get that energy is equal to minus Z e squared over 8 pi permittivity R. So equation 28. So at this point, we have introduced the radius of the atom into the equation. And so we got the last part where now we want to substitute R by the big expression for R that we derived. Okay, so we go ahead in step 3, we substitute R by the value of R, which was h squared permittivity n squared over pi m e squared z. So where we had R in equation 28, we substitute this value, this expression here. And so if we do that, we get expression 29, equation 29, which says that energy of electron in an orbit is equal to negative m, which is the mass of electron, times e raised to 4 z squared over 8 pi, h squared is permittivity squared n squared. So equation 29 is important, and we see we can pull together the constants to one side and then the variables at the end. So negative m e raised to 4 over 8 permittivity squared h squared times z squared over n squared is the equation that can be used to calculate energy of electron in a given orbit. So we substitute the values of the constants to give us a particular figure that we need. Then we leave the variables which will be changing as electron move from one energy level to another energy level, and also as we move from one element to another element, the value of Z will change. So we substitute the value of M, mass of electron, the electronic charge, which is 1.602 times 10 raised to minus 19 coulombs. Remember that you put the value of the constant together with the symbol inside the bracket, then you apply the power. Divide by 8 times permittivity squared. The permittivity is 8.85 times 10 raised to minus 12 per joule, coulomb squared per meter. You square everything in the bracket. Then you have the Planck's constant, which is 6.626 times 10 raised to minus 34 joule second. Then you square everything in the bracket. So you work out the values of the constants, and you get energy is equal to minus 2.18 times 10 raised to power negative 18 Z squared over N squared joules per atom. Okay, so the final value you get, this is some books don't drive the equation, and they just give you the energy of electron in the first orbit of hydrogen is equal to minus 2.18 times 10 raised to power negative 18 joules. So remember, all the big values we had are reduced because they are constants. They will be reduced to this value. So what is changing in terms of energy as the electron move from one energy level to another energy level is the value of N. So as for the first orbit, the value of N will be replaced by 1. If the electron is in the second orbit, the value of N will be 2. So you'll have 2 squared. If you got the third orbit, the value of N will be 3. And so you'll have 3 squared. As you go to the fourth orbit, the value of N will be 4. So you'll have 4 squared. So in a particular element, we can use this equation to calculate energy of electron by, you remember that the element will be identified by its atomic number, which is the Z value. So for hydrogen, Z is 1. So hydrogen is Z is dependent on the type of element. Once you know the element, you use its value of Z, and now you go to look at the energy level in which the electron is, which will be affecting the value of N. So that is what you need to know. You can drive the equation, and you can master this negative 2.18 times 10 raised to minus 18 as the energy for the first orbit of hydrogen. So the second orbit, you will have the value of N will be 2. So you substitute N squared by 2 squared. The third, you substitute N squared by 3 squared. Now, we see that the energy of electron has a negative value. So we need to note that the reason why the energy of electron is negative is because electron in an atom is lower than the energy of electron in the atom is lower than the energy of a free electron. Free electron is the one that is not bound by the nucleus of the atom. So usually, to bring electron to lower energy level, you are moving from high energy level to lower energy level. So electron continuously loses energy. And so as it loses energy, its energy becomes negative. As your electron moves to higher energy level, it gains energy. So it becomes more and more positive. And then when it's completely out of the atom, its energy will be zero, meaning that it's no longer bound to that particular nucleus. So we know that the most stable stationary state of electron corresponds to when the value of n is equal to 1. That is the most stable state for hydrogen. Then as the electron gains more energy, it goes to n is equal to 2, n is equal to 3, 4, and so on, depending on the amount of energy it has absorbed. But those will be unstable or excited states. So as n value increases from the lower energy level to higher, the energy decreases in absolute value and approaches zero. When it is zero, it means that the electron is not bound to the particular atomic nucleus. And so it means that the atom has completely lost it, and we call that the atom has been ionized. You can be able to calculate using the value we have derived. You can calculate energy for another energy level very easily by doing a simple manipulation that we are showing on the screen to end up with a simple equation. So when you need to calculate energy of any other orbit or energy level, you remember we assume that we don't know the exact energy value level, so we put En. And then the one we have derived is for the first energy level, so it is E1. So we see for the energy for a known orbit, we can represent that unknown orbit by n. And we have the first one, which I've already derived, is E1. So we divide En by E1 to get the equation we have on equation 31. When you divide En by the expression for E1, you get the expression we have on equation 31, whereby that other energy level you want to determine will be given by the value of energy level 1 times z squared over n squared. That means, if you remember, I told you to master the negative 2.18 times 10 raised to minus 18 z squared over n squared, and that will now give you the value that you need to calculate for any other energy level, which is also given in equation 31. So here, suppose you are asked to calculate the energy for second orbit, you just put where you have En, you put E2. And then you come to this equation, you have substitute the value of Z and the value of N, which will be 2. So it will be 2 squared. Then you get the equation, the value straight away. Do you have any question up to this point? Collins?
Excuse me.
Collins. Go ahead.
The value of Z and N are they the same?
This is what you need to note now. The value of Z will depend on the element. If you are asked for hydrogen, actually Z is the atomic number which identifies the element. So if it is hydrogen, Z, you are supposed to know that atomic number for hydrogen is 1. If you are talking about helium, you must know that the atomic number for helium is 2. So Z will change depending on the element, okay? Now within the element,
Okay.
you get energy levels. So depending on which energy level the electron is, the value of N will be now adjusted accordingly. That's why I said Z and N are the only variable that you need to mark, because the other variables in the equation for
We mnasikia like?
Hapana. Hapana.
Sir, we can't hear you.
Has muted himself.
We can't hear you.
Maybe network yake imeenda.
Stop sharing.
Hadi screen sioni.
So you have stopped sharing.
Kwani Leka ameenda Diwali?
Anaweza kuwa amejileftisha.
So there was discussion, but I think something happened to the setting for the Microsoft team. So it is saying that the meeting is general and another device was coming in, so but we can continue. So I think the recording is what might disappear. But I'll give you the recording for the other group in case that happens. So we continue with presentation. I'll go back to it. There was a problem there. So I was saying that in the equation for energy, the value for first orbit is important. It is negative 2.18 times 10 raised to minus 15. That value is constant, so you must know it. Then if you are talking about hydrogen or helium, you have to know the value of Z will change. But when you have already identified the atom that you are dealing with, then what you should worry now is the value of N, because N will change depending on whether electron is in the first orbit, second orbit, third orbit, and so on. So these are very simple, although the derivation can look a bit confusing, but if you work through several times, it becomes easy. So yes.
At the beginning of the derivation of the energy equation, you stated that kinetic energy is added to potential energy, but then I was seeing we were subtracting.
Give me 1 minute. 1 minute. There's a phone call from the department.
It's too dangerous, man.
Kwani Leka ameenda?
Hujasikia kuna phone call from the department.
Yeah.
Zingine simu zinalia kasi hizo.
Mnyamaze, kuna Wahindi wanataka kusoma hapa.
West Wendell Alliance.
Bwana, hiyo assignment ilikuwa kwa hii class. Umeiva. Hiyo assignment ilikuwa kwa hii class, umefanya aje?
Unasema
Eh?
nini?
Na
Tumefanya na vitabu na kalamu.
So we can continue.
limekataa kuongeza.
We can continue, and please remember, I have always told you this, that always mute your microphones, because after my lecture, I'm supposed to send you the recording, but now if the recording is full of noise, you cannot even hear what was being said. It is a bit difficult. So always avoid a lot of noise in the background. So we are looking at the equation for calculating energy, and somebody was asking question. So please come up again.
I was saying at the beginning of the derivation of the energy equation, you said that the kinetic energy is added to the potential energy. But then I was saying they're being subtracted afterwards.
Now the potential energy as a sign of negative. So plus minus is negative, is still minus. That's what affected there. The sign for potential energy has a negative value. Okay. Next question, please.
Excuse me, sir.
Yeah, go ahead.
Is the potential energy negative because of the value? Because the electron is already dislodged from the atom?
Is the potential energy negative because of?
The electron being dislodged from the atom. The electron is part of the atom.
Okay, first of all, we need to distinguish from the energy of electron and the value of the potential energy. Usually potential energy is negative because to reach a position where you are, you lose energy. To be stationed at any particular point, you see, when you go up, potential energy increases. As you come down, potential energy decreases. So that's why the potential energy sign is always negative. But for the electron, remember we said that the value of energy of electron is negative because away from the atom, you approach zero. So we are connecting this to the influence of the nucleus to the electron. So as the electron moves away from the nucleus, its energy increases. Okay, it increases in terms of becoming more and more positive, or it's becoming less and less negative. But as it comes close to the nucleus, you see it's moving from a high energy level, and as we saw in the emission and absorption, that as you move from high energy level, lower energy level, energy is given out. So you lose energy. Okay. So that's what's happening to the energy of electron. As it goes down to the lower energy level, it loses energy. So its energy is negative compared to the free electron.
Thank you.
There are people who have unmuted and there's a lot of echo in the background. So we have I-20 2614. I don't see your name, but you can raise your question. 2614. It's not asking. So we can proceed. So we substitute values here to try and calculate energy. So here we look at energy involved in exciting electron from the lowest energy level to energy level infinity. Infinity means that the value of n is very big. So we use the symbol infinity. So this means that when you transfer electron from the lowest energy level where it is to infinite energy level, it means that electron is completely removed from the atom. So that's when you put a positive charge to signify electron lost, because you have more protons now than electrons. So to transfer energy electron to infinite energy level, we can calculate the energy required from the value we have already established. So to do that, let's see if the electron is in the first energy level, and then you are transferring to energy level infinity. So we have the first equation for the first energy level, then the second equation for infinity energy level. Then we need to subtract the energy change. So the energy change is equal to energy of infinity energy level minus energy of the first energy level. So we see that in the manipulation on the right hand side for each equation, we know the energy for the first energy level will be equal to negative 2.18 times 10 raised to power negative 18 joule per atom, whereas the energy for infinite energy level, when we substitute in this equation, when n is very big, the equation reduces to 0. It is when you divide a number by a very big number, the final answer is close to 0. So we put 0. The energy for infinity is equal to 0. So we subtract the energy for infinity minus the energy for first level. So you end up with plus 2.18 times 10 raised to power negative 18 z squared over n squared joules per atom. What this means is that the value is going to be the same if you are going to knock out electron from the first energy level completely out of the atom, but now the sign is not negative, the sign is positive. The implication is you have to provide this energy to the electron in order to remove it from the atom. So this is called ionization energy, because to ionize is to completely remove electron from the atom, and so to do that you have to provide energy, or the energy is required. So there's implication of the positive value for this energy. Okay. Now, if we go to the periodic table, we can also be able to analyze the trend in the ionization energy of electron. So let's look at the first period, or just within the period. As you move from the left hand side to the right hand side, we see that the value of Z is increasing, but the value of N is the same. So it means that as you move from the left hand side of the periodic table to the right hand side of the periodic table, ionization energy will increase. So it means that you will require more and more energy to knock out electron from the atom as you move from the left to the right hand side within a period. Then as you go down the group using this equation 32, we see that the Z increases and N increases, but the value of N is increasing very fast. So we see that there will be a decrease in ionization energy as you move down the group, because the energy levels are increasing, and we can explain that by, as the electron is occupying the higher energy level, the force of attraction from the nucleus is decreasing, and we are going to look at that later again to see why it decreases. So the nuclear charge that will be felt by electron in higher energy level will be less compared to the one where you have, say, first energy level. And that affects ionization energy. So since we have a less attraction to the nucleus, you'll find that ionization energy will be less. Yeah, you have a question?
Your slide stopped moving.
They stopped moving?
Yes.
So what I'm going to do is to stop sharing and then to load it, okay? Probably. You can see it now?
Yes.
Yes. Yes.
So we
Yes.
go to now this diagram,
Excuse me, sir.
which shows the hydrogen line spectrum. Hydrogen line spectrum. So the lines you are seeing labeled 1, 2, 3, 4, 5, 6, 7, up to infinity represent the energy shells in the hydrogen atom. So if you can, although we are putting it on the straight line, remember this could be like the circles within the hydrogen atom as the electron move from energy level 1 to 2 or to 3 to 4 and so on. So we note that when electron falls from high energy orbit to lower orbit of hydrogen, emission spectrum is produced. So we saw how the emission spectrum of hydrogen looks like. And so we want to try and understand the values on this diagram. So we see that when electron move from energy level 2 to energy level 1, you will see in the spectrum of hydrogen at wavelength of 121.6 nanometers. But if it is from the third energy level to the first energy level, you will see the wavelength of 102.6. From the fourth to the first energy level, you will see a wavelength of 97.3. From the fifth, you will see 95.0. So in summary, the hydrogen spectrum consists of bands or series of wavelengths representing transition of electron from high energy to lower energy. So we have a series of wavelengths when the electron is falling from high energy to energy level 1. When it's falling from high energy to energy level 1, these series of wavelengths are called Lyman series. So if I ask to calculate energy or wavelength when electron falls from second energy level in Lyman series, it means electron is falling to the energy level 1. So I don't need to tell you that it's moving from energy level 2 to 1. I can also ask you calculate the largest wavelength when electron transits in the Lyman series. So the largest wavelength is where you have the smallest energy change. And we see the largest wavelength will be related to transition from n is equal to 2 to n is equal to 1, and you get 121.6. But when n is equal to 3 to n is equal to 1, we see the wavelength is decreasing as you move from higher energy to energy level 1. This is also can be calculated. The wavelength shown here can be calculated when you take the energy difference that we have. For example, energy for level 2 minus energy for level 1, you equate it to H to delta E, which is equal to H nu, and which is also equal to Hc over lambda. When you calculate the value of lambda, you will get the value shown on this spectrum. Okay. So in this case, we can relate the spectrum of wavelengths that we see to the transition taking place within the atom. And that's what we told you, that from the spectrum, you can be able to identify the element present in the material, because these wavelengths are unique for each type of element. They will be unique for each type of element. And so you can be able to identify which material is present. I continue with the second transition series. So you can also have transition where electron is moving from higher energy to energy level 2. This is called Balmer series. So it is moving from higher energy to energy level 2. For example, it can be moving from 3 to 2, or 4 to 2, or 5 to 2, or 6 to 2. Okay, so you see these wavelengths are different also from the one we saw in the Lyman series. If electron is moving from the higher energy to energy level 3, we call that past tense series. And also we see they have different wavelengths. Are you seeing that? So in the past tense series, we move from either 4 to 3, or 5 to 3, or 6 to 3, and so on. What you need to note in doing this, what you need to note is the final energy level where the electron goes. If the electron is going from higher energy level to energy level 1, we call that Lyman series. If the electron is moving from higher energy level to energy level 2, we call that Balmer series. If it's going to energy level 3, we call it Paschen series. If it's going to energy level 4, we call it bracket series. And then if it's going to energy level 5, we call it Fund series. So it's important to realize the application of these names of the people who discovered the spectra of hydrogen atom. So the series are named upon the scientists who discovered this series. Do you have any question here before I continue? Because we are winding up Bohr's atomic model.
I have a question on ionization energy.
Yes.
You said that it increases across the period and decreases down the group. Now, when it is increasing across the period, will the Z be, will you use Z as a number of protons, and then when it's decreasing down the group, the Z will be number of electrons?
No. No, because you know that from your high school chemistry, science doesn't change many things. We said in high school that Z is atomic number. Even the university, Z is means atomic number. Okay, Z represents atomic number, which is used to identify the element. So we know that as you move from the left of the period to the right hand side of the period, the elements are changing. Okay, that means the Z is changing, but the electrons are going to the same energy level, which is represented by the value of N. So N is the energy level. So within a period from left to right hand side, the elements are changing, but the energy level in which the electron is occupying is the same. The implication here is this: as the atomic number increases, the number of protons in the nucleus are increasing, so the nuclear charge is becoming more and more positive and attracting the electrons. But the electrons are occupying the same energy level, so they experience more nuclear charge and are pulled much closer to the nucleus. Okay, that's why we saw that even in the same period, moving from left to right hand side, also the atomic radius decreases because of the influence of the nuclear charge. So that is what is causing the ionization energy to increase, because of the increasing nuclear charge pulling electrons, and so you need more energy to remove electron from that shell. Okay, because you need more energy to remove electron, ionization energy will do what? Increase. But when you move down the group, remember, you are changing the element, but also the energy level is changing. Okay, the energy level is changing, so the value of N is increasing, and so the electrons are now occupying energy levels which are far away from the nucleus. Therefore, the amount of nuclear charge that they now experience is less. Okay, it's going to be less, and because of the less nuclear charge binding them to the nucleus, you need less energy to knock out electron, and that's what explains why the ionization energy decreases as you move down the group. Moving down the group is similar to moving to higher energy level. So electrons are occupying energy levels which are far from the nucleus.
And why is the value joules and joules per atom and not joules only? And it is energy.
You see, electron, we are talking about electron in a single atom. We are not talking about many atoms. That's why it is per atom. But if you're talking about a mole of particular element, you will need to multiply it by Avogadro's number. Okay. If I ask to calculate the energy,
okay.
Here. I don't know if there's another question. Let me confirm. Yes, we have Clinton.
Yeah.
So just give me, Clinton, just give me a few minutes. I completed this particular lecture. Tomorrow we start with another one, so that we make progress, and then you ask after I finish presenting this. So we see here, we have finished interpretation of hydrogen spectrum, where we have many series, which you need to know. We have the Bastian series, the Balmer series, we have the Lyman. You need to know what they mean. So you can calculate. Unfortunately, I can't introduce this now because it's going to mix you. So we'll stop on this slide. Tomorrow I will introduce the next slide because it's a bit wide. Okay, so you can go ahead to ask your question. Clinton.
How is energy? Is energy 2 is stronger than the energy 1? Why?
Why is energy 2 stronger
Yes.
than energy 1?
Yes.
So there are two things that you need to take note here. So you see, look at number 1, 2, 3, 4 as you go up. That's right. Now
Yes.
look at them very carefully and look at the power. Look at the power. It is becoming negative 18, then negative 19, then negative 19, then it's going negative 20. That's right.
Yes.
So if you look at the value magnitude, it is becoming less and less negative. Is that okay?
Yes.
So it's becoming less negative, which means when it's becoming less negative, it's becoming, we can say it's becoming more and more positive. Is that right?
Yes. Yes.
When it's becoming more positive, so we can say the energy is increasing as you move from lower energy level to higher energy level. That is the interpretation that you need to get. That is becoming less negative or it's becoming more positive. So energy of electron is increasing as you move from lower energy level to higher energy level. And increasing is approaching zero. So at infinity, that's why we put this infinity energy level. At infinity energy level, the value will be zero. Interpretation being, it is no longer bound the nucleus. So there are two things that you need to note. Okay?
Yeah.
Next person.
Question
Yes.
about the energy levels. You said that the